All right, we're ready to get started. Sorry I was a little late. Uh, I ran out of regular milk for my coffee, and so I'm having to use oat milk, which is clearly far inferior. So if I'm a little bit irritable today, that's why. Okay, so I actually do like vegan food, but real milk in my coffee is essential. Okay, so when we wrapped up last time, uh, hopefully you can hear me on Zoom. Somebody tell me if you can hear me on Zoom. Great. All right. When we finished up last time, we were talking about quorum consistency or quorum systems. And this question about if a client is talking to several replicas, how many replicas should they talk to? Should they talk to both for reading and writing? So this is the picture that we drew at the end of last time um, for that. So we were considering a system with three replicas and and trying to figure out what would make sense for the client to talk to. Say that they wanted to have strong consistency. Say that we wanted to make sure uh, that that replicas agreed and that the client wasn't able to observe any replication anomalies. If that's what we wanted, then this strategy of read one, write all would work. So we could say three replicas, all of the replicas have to acknowledge a write operation. So the client writes to all three, and the write's not considered to have committed until all of them acknowledge it. But for a read, the client only has to talk to one. Um, so that's one way of configuring things, and it's very popular. The trouble with this, of course, is that it's not fault tolerant in the sense that if a node crashes, then you can't do a write at all. Or if there's a network partition that separates some nodes from the client, then you can't do a write at all. No write can commit. Of course, other strongly consistent replication strategies like primary backup and chain replication have the same problem as we've seen. Um, so, so this is a problem. Well, it may not surprise you to learn that read one, write all is not the setting that the Dynamo paper suggests using. So, in fact, when you have three replicas, uh, what did they suggest in the Dynamo paper? Does anyone recall? Sounds like somebody's mic is on. If you could mute yourself, please. So Zoom is acting a little bit strange for me. It just muted me, and I had to unmute myself. So I don't know how much of what I just said people heard. Um, Let me start over. Uh, so, so we're in this setting where we have three replicas, and we know that if we said that the write quorum was three and the read quorum was one, then then we would get something like strong consistency. We would get strong consistency. Now, before we define strong consistency as meaning the client can't observe that the data is replicated at all. So here the client is in fact talking to three different replicas. So they do know in some sense that the data is replicated. But it is strongly consistent. It would be strongly consistent in the sense that the client can't observe any replication anomalies. So that's what we would get if we had this setting of setting the write quorum to 3 and the read quorum to 1. But that has problems in terms of fault tolerance. And also writes are slow. So what does the paper suggest doing instead? Hmm. More Zoom issues. Let me try this again. How's that? Great. Sorry about the technical difficulties. Yeah, so we're not even, so somebody asked a question that had to do with the ring of nodes. So you're actually jumping ahead of a little bit. So we're going to talk about that a lot. But even before we get to that, we can talk about this question of how big the read quorums and write quorums need to be. So, okay, so the Dynamo paper has a suggestion. They suggest setting the read quorum to 2 and the write quorum to 2 when we have 3 nodes. So what would happen then? Well, okay, let's say we do a write of a particular key and then we read it. Well, something like this could happen. So we have our 3 replicas. Client does a write to 2 replicas. They both acknowledge it. And then the client asks what the value of x is. Well, because the write quorum is 2, the client might see a stale value of x over here, right? Let's say that x was 4 over here. So if their read happens to hit these 2 replicas, then they'll get some different values for x, right? They'll get that x is 5 and they'll get that x is 4, or whatever this replica over here thought that x was. But there is some guarantee that you get right. Because the read and the write quorums overlap, you know that you're going to get at least one response that has the latest write. Now, you may or may not have a good conflict resolution strategy. Over here on the client, you're going to find out that one replica thinks x is 5 and that another one thinks x is 4, and you have to figure out what to do about that. But at least you know that you're going to see the most recently written data in at least one of the responses that you get. Now, sometimes R is defined differently. So here, I'm defining R as being the number of replicas that have to acknowledge a read, and W is the number of replicas that have to acknowledge a write. Now, in some settings, if R is 2, then that would mean you have to hear back from at least 2 replicas with the same value. I've seen it defined that way in some places, but I don't think that that's what the Dynamo paper means by it. I think they just mean 2 replicas have to acknowledge the write, and they might come back with different values. So in general, here there are 3 replicas, so n here was 3. In general, if we ensure that R plus W is greater than N, then we know that every read quorum is going to intersect with every write quorum. And we won't get what's known as a stale read, where all of the responses that we get back are too small. So in particular, if we had chosen a read quorum of only 1, if we'd had a write quorum of 2 but a read quorum of 1, then we could have been doing our writes to replicas 1 and 2, doing our reads from replica 3, and we would never see any of the writes that we had done. So this is the inequality that you need to know for figuring out how to set R and W. Of course, if you choose that read one, write all setting, so in this example, then read one is, so R would be 1 then, and W would be 3. So this, of course, satisfies this property because N in that case is 3. So the read one, write all setting would satisfy that property, but so would this other setting where you only read 2 and write 2. Now this wouldn't give you strong consistency in the sense that you would still be able to observe that these two replicas had different states, but you would at least have this property that somebody's going to send you the most recently written data. And this is indeed the setting that a lot of systems go with, and this is what they use for the experiments in the paper. There's a lot more to say. There's more to say on quorum consistency, but that's the short version. Somebody asked what was wrong with doing read one, write all. Well, it's slow, right? If I had to wait to get every replica to acknowledge me before a write had committed, then that would be slow. So it's the same problem that we see happening with the other strongly consistent replication strategies that we looked at, like primary backup and chain replication. So so any time you want to ensure strong consistency, it's going to be slower than if you aren't ensuring strong consistency. All right. So that's all I really want to say about that. That's the short version, quorum consistency. I want to move on to something new today. So we're going to start talking about sharding today, also known as data partitioning. Not to be confused with network partitions. So network partitions are when some nodes can't communicate with other nodes. Data partitioning has to do with how you split up your data among nodes. Different thing. It's one of those annoying situations in distributed systems where we're using the same term to mean totally different things. Okay, so we've spent a lot of time talking about replication, right? Which is having multiple copies of the same data on different nodes. And in the systems that we've talked about so far, every replica stores all the data. So you might have a bunch of different machines, and let's say it's a key value store. You have a bunch of different key value pairs. And every replica has all the key value pairs. And so your clients are over here talking to replicas. Are there any problems with doing it this way, with putting all the data on all of the replicas? What do you think? Yeah, lots of good suggestions. So, so scalability is mentioned. So yeah, maybe if you have more data than can actually fit on a single machine, then maybe you can't do this, right? Um, let's say you have you can scale up an individual machine to a certain point, right? But at some point, that becomes much more expensive than just having more than one machine. And then there's this. Let's say you're doing primary backup, for instance. That means all of your reads and writes are being served by one machine, the primary. So if you have lots of clients making lots of requests, then the primary has to do a lot of work, and you can't just talk to the backups. So that's kind of what I've illustrated here. Say these clients are talking to this machine. Maybe this machine here is the primary. But what if you did this? So now you've split up your data across these machines. And they don't have to be kept consistent with one another, right? Because they're all storing totally disjoint parts of the data set. Of course, now we lost replication, right? We only have one copy of each, so we don't have fault tolerance. But we could put it back. We could call this M11, M21, and M31, and then we could have some other machines here. Okay, so now we have replication again, and we've also split up the data set among multiple machines. So splitting up the data set like this among multiple nodes is known as sharding or data partitioning. So we've got shards like this. Also sometimes known as replica groups. So why would you do this? Well, one reason might be to improve throughput, right? Now, if you have clients that need to read all this data, right, and the requests are more or less split up evenly across the space of key value pairs, then it might make sense to have several machines serving those requests instead of just one. And then the other reason, of course, is if you just can't fit all your data in one node, then you might need to split it up. So reasons to do sharding include improving throughput, and storing large amounts of data. So in this example, I split up my data set into 3 shards. So I'm pretending that we're only storing one key value pair per shard. And in practice, you'd have a whole lot on each shard. But in any case, you would have a disjoint set of them on each. But it would also be possible to have a different design. It would be possible to have the data partitioned or sharded, but to have more than one partition per node. So for example, we could do this. We could have something like machine 1, machine 2, machine 3. And then our clients over here. So now we have 3 machines, like we started with, but the setup is a little different, right? We have replication. So for example, we have 2 copies of key X, 2 of key Y, and 2 of key Z on different machines, so we get fault tolerance that way. But we're also splitting up the requests. So let's say that Z is getting a lot of requests. So, and then let's say Z is getting a lot of requests and X and Y are getting a lot of requests. Maybe it makes sense to have Z stored in a different place than X and Y, so you can split up the load of requests that have to be served. So this way, as you can see, these replicas still have to be kept consistent with each other per key, right? So this replica has to be able to keep consistent with this replica's X. So there has to be communication between these replicas here. And it has to keep consistent with this replica's Y. So there has to be back and forth conversation here. And similarly here. And in fact, the way that you might design it would be to have each replica acting as a primary for some part of the data set and acting like a backup for another part of the data set. So let's say that this replica M1 is the primary for key X, so I'll put a P there. And then this one over here is the backup for key X. So requests for this key would go here. And then for Y, M1 would act as a backup, but this machine down here would act as the primary. And for Z, M2 would act as the primary, and this machine would act as the backup. So every machine is playing the role as a primary for some part of the data set and as a backup for another part. This helps split up the workload, right? So if the clients need X, they talk to this machine. If they need Y, they talk to this machine. And if they need Z, they talk to this machine. But we still have replication in the sense that the data is stored on different independent machines. So this is kind of nice, right? I managed to split up the request load coming from the clients, but also have replication. So each machine is storing here 2/3 of the full data set, right? So this also could help solve the problem, although not necessarily in the same way that we did before, but it could help solve the problem of not being able to store the whole data set on one machine. So every machine has 2/3 of the full data set. So this is another, this is also sharding. So sharding is important. It gives you better throughput because you can serve different parts of your data set from different machines at the same time. And it makes it possible to store a data set that's too big for any one node. Now, if you're not using a strongly consistent replication strategy, like Dynamo, then maybe you already were serving requests from different machines at the same time, right? So Dynamo does this. But you definitely still need partitioning, or you definitely still need sharding if you want to serve these sorts of larger than can fit on one node data sets. So real systems are typically going to do both replication and partitioning. So putting this this picture back here. So we can kind of think of this data set as being, or these replicas as being split up two different ways. So X is being replicated across these different groups of machines, and then each of these groups of machines together stores all the data. So the choice of the partitioning strategy, or the choice of the sharding strategy, is mostly orthogonal to the choice of the replication strategy. So in our discussion today, we're going to mostly ignore replication, and we're just going to focus on partitioning. So in my diagrams, I'll mostly just draw the partitions, and you can assume that they're replicated somehow. So I'll be focusing in on the partitions, like how the data is split up among nodes. And you can assume that there's some replication of those, but how they're replicated is not going to be our concern for the moment. So let's take away the replicas from this picture, and just focus on partitions. Oops. And clients may talk to multiple different partitions. It depends what data they want. Okay, so say we have this large amount of data. We want to partition it. How do we decide which data to put on which nodes? So let's continue to imagine that the data is these key value pairs, a simple data model. So which key value pairs go where? What would be a strategy that you might use? Or let me phrase it this way. What goals are we trying to accomplish with our partitioning strategy? So for sure we want the data to be evenly distributed. Good. Not much use in doing partitioning if it all ends up in one place, right? We want to do that so that we avoid hotspots, right? But yeah, right, great point. We also want it to be easy for the client to find. We want it to be fast and easy. So these goals kind of feel like they're in tension with one another, right? Like if we put all the data on one node, then it's really, really easy for the client to figure out where to find it, right? They know it's all there. But on the other hand, that kind of blows apart our goal of trying to evenly distribute the data. So we want to evenly distribute the data, but we also want it to be easy for the client to find the data. Let me throw out another possibility. If we just randomly assigned key value pairs to nodes, then that would probably do a pretty good job of spreading out the data. But it would also make it very hard for the client to find the data that they wanted. So neither of those are great ideas. So we could sort of make a little table here of the options. So if this is goal 1, this is goal 2, So if we choose randomly distributing the data, then it'll end up being evenly distributed, more or less, but it definitely won't be easy for the client to find what they want. And if we don't partition at all, we put it all on one node, then sure, it'll be easy for the client to find, but it won't be evenly distributed at all. So those are both bad ideas. So what else can we do? So a good suggestion was made actually a little while ago in chat, that had to do with hashing the keys. So before I talk about that, just as a straw man, let's think about another possibility. We can say every partition will store a particular range of the keys. So this is called partitioning by key range. So for instance, if my keys are some sort of alphabetical strings, then I could say that M1 is responsible for A through H, and M2 is responsible for I through R, and M3 is responsible for S through Z. So maybe we have like B equals 3 here, and I'm trying to remember the alphabet. P equals 5 here, and Y equals 4 here. Something like that. Okay, so this seems to work, partitioning by key range, and some systems do something like this. But what's the downside of doing it this way? Right. What if this is how you set things up, and then the writes start coming in, and they're all like, oh, S equals 10, and Z equals 5, X equals 9. So you'd end up with this uneven distribution of data because your keys were not uniformly distributed across the space of letters. So now your data is unevenly distributed across the servers. So key partitioning by key range probably is not a good way to go unless you had some way of knowing in advance that your requests were going to be adding a uniform distribution of keys or requesting a uniform distribution of keys. But there's hope, right? We can solve this problem really, really easily. What is a way to take data that's not uniformly distributed and make it uniformly distributed? Hashing, right? A hash function. So a good hash function will take our possibly wildly uneven distribution of keys and will distribute them evenly across its output space. So let's take MD5, for instance. So MD5 is a function from its input space to its output space. Its input space is going to be the keys in this case. So, and its output space is going to be numbers from 0 to, so MD5 returns a 128-bit hash, right? So this is going to be 2 to the 128 minus 1. So strings are keys, probably with some fixed length limit. We hash them with MD5, we get outputs in this range, and they'll be more or less evenly spaced over that range. So if our input strings are like, no, maybe that'll get hashed to here, aardvark, it'll get hashed to here. Platypus will get hashed to here, maybe. ZZZZZ, it'll get hashed to here. What's an animal that So the hope is that even if your keys aren't evenly distributed across the input space, the output of the hash function will be. So, okay, then we have a way to distribute the keys evenly across the nodes. We just give every node an evenly sized piece of the output space, right? So we might say, okay, machine 1 gets this piece of the output space. And machine 2 gets this piece of the output space, and machine 3 gets this piece. So one way to do, so that's the way that I've drawn it here, but actually the way that you might more likely do this is say, just take the output space of the hash function, and if you want to split over, say, 3 nodes, do mod 3 of the hashed value. So if I want to know where to put the key value pair, whose key is aardvark, then first I hash it to get this 128-bit hash value, and then I do mod 3 of that. The output of mod 3 is going to be 0, 1, or 2, and then that's going to tell me which of my 3 nodes to put the key value pair on. So this is actually the wrong picture to split it up this way. It would actually be more like individual stripes, where like 0 here hashes to M1, and 1 hashes to M2, and 3 hashes to M3, or 2 hashes to M3, and so on. So this is a good approach because if I want to look up a key and I need to know where to find it, I just do the same thing. I calculate its hash and then do mod 3. Or mod n for whatever number of nodes that I have. And this could be done either on the client side or on the data store side. So a better approach than simply splitting by key range is this hash of key mod n approach, where n is the number of shards that you have. So this is good, but what's the catch of doing it this way? Can anybody think of any problems with using this approach? Yeah, okay, and hash collisions, but I mean, we're not going to worry too much about that, right? We're going to assume that we have a reasonably good hash function. So, okay, it might not be perfect, but collisions aren't our primary concern with doing it this way. So a great point was just raised in chat, which was that this is not necessarily resilient to replica failure. Okay, so what could be the problem? Well, what if the number of nodes changes, right? So in general, in distributed systems, we want to be able to address the problem of things changing over time, right? Maybe we're getting more queries, right? So we want to be able to add a machine to let us handle all those queries. Or our data set grows, right? And we want to add a machine to help store all the data. Or a machine fails. And we want to be able to keep on accepting writes to data that happen to be in a shard on that failed machine. So the trouble with doing this hash of key mod n thing is that if n changes, most of the data gets moved around. So let's say n changes from 3 to 4. Let's say that we added another machine here. So we had 3 machines, now we have 4. Before we did MD5 of aardvark, and we got MD5 of aardvark mod 3, right? And we got, let's say, 0. I don't actually know what the MD5 of aardvark is. You can try it yourself if you want. But let's say that we did MD5 of aardvark mod 3 and got 0. Now we do MD5 of aardvark mod 4 and we get something else. Say we get 2. So now that key needs to move from machine 0 to machine 2. Or machine 1 to M1 to M3, because our indexing here was from 1. So that seems kind of messed up, right? If we added a new machine, it's understandable that we're going to need to move some data around, because when we add a new machine, we have to move some data to the new machine. But instead of moving data to the new machine, like let's say, so in this case, we added M4, right? So it would make sense that some data has to get moved over to this new machine M4. But as a result of using this hash of key mod n strategy, we moved aardvark from one old machine to another old machine. So that seems unnecessary, right? When we add a new machine, we shouldn't have to move data from an old machine to a different old machine just to accommodate the existence of this new machine. So in an ideal world, we would do the minimum amount of data movement necessary. So the trouble with this hash of key mod n thing is that if the number of nodes changes, then we end up having to do unnecessary data movement. I'll write that down. Okay. So that raises the question, what is the minimum amount of data movement necessary if we want the data to be evenly split between nodes? So let's say that we have 6 keys on 3 nodes. So about 2 per node, right? They might not be exactly evenly split, but let's suppose that they are. So let's put some keys here. Okay, so those are our 3 nodes. Now let's say that we add 1 node. So there are now 6 keys and 4 nodes. Here's our shiny new node. Because we have 6 keys and 4 nodes, how many keys should we have per node on average? Yeah, 1.5. 6 divided by 4, or 1.5. Well, we can't really move 1.5 nodes, or we can't move 1.5 keys. So we have to move either 1 or 2. Say it's 1. Okay, so say this key moves to the new node. So that's the minimum movement possible to achieve an even split. So in general, if you have some number of keys, k, here we had 6, but in general, if you have k, and you have n nodes, then how many keys do you have to move? In general, it's k divided by n. So That's the number of keys that have to be moved to ensure an even split, or a split as even as possible. I should say the number of keys that have to be moved to ensure an even split when n changes. So we would like to come up with a partitioning strategy that only moves k over n nodes. And we accomplish this using something called consistent hashing, which you might remember from the Dynamo paper. Consistent hashing. This is another one of those unfortunate distributed systems terminology collisions. So here we're using the word consistent in a totally different way from where we meant it before when we were talking about consistency models. Unfortunate collision, this is just what it's called. This idea emerged more from the networking community, so maybe that's why there's this, this naming collision. So the idea is that we arrange our nodes in a ring. So here's M1, here's M2, here's M3, maybe here's M4. And the points around this ring correspond to the output space of our hash function. So we were using MD5, right? Which we said had this huge output space ranging from 0 to 2 to the 128 minus 1. That's too big of a number to think about. So let's pick something manageable. So let's just say that the points around this ring correspond to 0 to 63. So here's 0, here's 1, and this goes around like this, and then here's 63. So in practice, this would be a much bigger number, but we'll pick a simpler number just for the sake of example. And then we can mark some other points around here. So like maybe this would be 16. Maybe M1 is at 8. Maybe M2 is at 20. M3 is at 32. Maybe M4 is at 47. So each of our nodes is going to belong to a particular point on the ring. We don't really care what point, but we calculate this somehow. Maybe we hash the IP address of the node using our hash function or something like that. And then the nodes will be more or less evenly spaced around the ring. Maybe not perfectly spaced, but more or less evenly spaced if our hash function has good behavior. Now let's say somebody wants to add a key value pair. Let's say the key is Apple. So we hash the key just like before. We hash the key of Apple, and let's say the hash function's output is 14. So we go to point 14 on the ring. There's probably not a node there. So what we do is we walk around the ring clockwise until we hit the first node. In this case, it's M2. So the key Apple gets stored there. So a key belongs on the server that is its successor on the ring. So if somebody wants to look up a key, same deal. If you want to look up apple, you hash the value of the key apple, you hash the key, you get 14, you walk around the circle until you hit a node, and that's the place where you're going to find the key that you wanted. And the circle wraps around. So let's say that let's say that I'm trying to look up the key aardvark. And let's say that aardvark hashes to 62. So on what machine will that key be stored? Right, it'll be on M1. So in Dynamo, they also use this ring to decide where to replicate things. So let's say that the replication factor is 3. That means that everything has to be replicated 3 times. The way that they do it is, for any key, it has a home node, which is the node that it hashes to using this approach that I just sketched out here, and then you store it there. So apple gets stored here, but it also gets stored at the node after that and the node after that until you have it stored in 3 places. So you could choose different replication factors. If you chose a replication factor of 2, then it might just be stored here and here. So that's how they choose where to replicate keys. So in Dynamo, every node has what the paper calls a preference list, meaning the places where that node's data will be replicated to. And the preference list will actually be longer than 3. Say if 3 were the replication factor, the preference list would actually be longer than that. Does anybody remember why the preference list is actually longer? It's because nodes could be down, right, or unavailable for whatever reason. So they still try to replicate in however many places. If the replication factor is 3, then they'll try to replicate in 3 places. Even if one of the nodes where they're supposed to be replicating is down, they just keep going down the preference list until they find 3 nodes that are actually up. And then later, if those nodes come back up, they might try to replicate to them. Okay, so we started talking about this whole consistent hashing strategy because we wanted to solve this issue of too much data getting moved around when we added or removed nodes. And we wanted to make sure that we moved as little data as necessary. So how does consistent hashing solve that? Well, let's add a new node to the ring. Call it M5. Okay, so I've added a new node here. Let's say it's at 60. So now that I've added this new node, which keys do I have to move? So what are the ranges that keys store? Well, we said that keys belong on the node that is their successor on the ring, right? So the keys that come from, let's see, 9 to 20 are going to go on to M2. M3 is going to get the ones from 21 to 32. M4, well, what did M4 have previously? It got, M4 got everything from 33 to 47. And what did M1 have previously? Well, before this M5 got added, M1 was responsible for this whole space, right? They were responsible for everything from 48 up to 8. But then we just put in M5 here. So which part of M1's key space does M5 now take over? That's right, yeah. So M5 is now responsible for this chunk of keys right here. So now M1 is only responsible for, I guess, 61 through 8. So now that we've added this new node of M5, which keys do we have to move? The only ones that we have to move are the ones that are in this range, from 48 to 60. And where were those stored before? They were stored on M1. So M1 is going to have to take, this whole range here was what M1 was responsible for before. M1 is going to have to take a chunk of its data and hand it over to M5. But on average, it will only have to move that K over N number of keys, where K is the total keys that are stored, and N is the number of nodes. And these other replicas over, or these other, sorry, not replicas, these other nodes over here, M2, M3, M4, they aren't affected at all. They can be totally oblivious to the fact that all this was going on. So they don't even have to care that a new node entered the system. So that's great. It's great when you don't have to care what's going on in another part of the system in distributed systems. Okay, so that's what we do when a node is added. It takes over part of the key range from its neighbor. All right, what about when a node crashes? Suppose M2 goes away. Who's affected by that? So which node is going to have to take over, right? So M2 was responsible for these keys, right? It was responsible for the keys from 9 to 20. So now somebody has to take over. It's in particular, its neighbor, M3, has to take over for those keys. So M3 has to take those keys on. Now M3 is going to get this whole range. But these other nodes, M4, M5, and M1, are unaffected. It's business as usual for them. This actually works really nicely in Dynamo, because whatever keys are being stored on a node, as the home node for those keys, they're also being replicated onto its successors. So if a node crashes and its successor node has to take over its part of the key space, then hopefully it has the backup already. So it can just say, okay, those keys that I was serving as a backup for, now they live here. I'm their home now. And of course, at this point, whoever's operating this system will probably want to bring another node up. But until they do, the neighbor node will pick up the slack for them. And that's consistent hashing. All right, we have 4 minutes left and I haven't done the quiz yet. So let me put up the quiz, and I'm actually going to leave it up longer than the end of class, just so that everybody has time to do it. Okay, so I'll leave this open longer than the end of class, but we have about 2 minutes left, and I want to talk about really briefly a couple of ways that consistent hashing might go wrong. So, can you think of any ways that this consistent hashing strategy might go wrong? And don't worry about doing the quiz immediately, because I'll leave it up for a while. Yeah, so somebody's suggestion is a node could take on a range that's too large for it to handle. Yeah, so that could happen if the nodes are not evenly spread around the ring. So that could happen, right? We know that a good hash function is going to map its inputs over its output range as evenly as possible. But if you have not very many inputs, then you can't necessarily expect the output space to be evenly covered. The more inputs there are, the more likely it is that you'll get this even distribution. So actually, a trick that you can play is actually have each node be hashed to several points in the ring. So a node, instead of just being hashed to one point in the ring, that node might pretend to be 30 nodes or 80 nodes. And each one is going to have its own identifier, which gets hashed to a position on the ring. And this makes an even distribution more likely, just statistically speaking. So those 80 or however many nodes they are called virtual nodes. So virtual node is virtual nodes are when a node, a particular physical node is hashed to many points on the ring. And the other thing about virtual nodes, in addition to improving the distribution of nodes on the ring, and this is an advantage that they actually bring up in the Dynamo paper, the other nice thing about virtual nodes is that you could have a different number of virtual nodes per physical node to account for differences in storage capacity on the physical nodes. So let's say you have a machine and it has like a 1 terabyte hard drive. Maybe you give it a certain number of virtual nodes. Maybe you give it like 20 virtual nodes. Another machine has a 2 terabyte drive, so you can give it 40 virtual nodes. So the machines that have more capacity can then be responsible for bigger slices of the space of keys. Yeah, there's the dot cam again, sorry. So virtual nodes are when a physical node is hashed to many points on the ring. So that's what virtual nodes do for you. They both allow the nodes to be more evenly distributed around the ring, and they also have this nice side benefit where you could have a different number of virtual nodes per physical node depending on the storage capacity of those physical nodes. We're almost out of time, but just really briefly, I want to mention a downside of using virtual nodes. So one is that if a node that's represented by many virtual nodes goes down, then lots of separate areas on the ring are affected, right? And lots of nodes would have to step up to be responsible for those parts of the ring. But in the Dynamo paper, they actually advertise that as a feature. They say that if a node dies, it's good to have its load spread out, right? Rather than just have its immediate neighbor take it on. So I can see why that would make sense. But it's maybe a little bit harder for us to reason about. So a nice thing about not using virtual nodes is that it's nice and obvious what happens if a node dies, right? Its neighbor takes on its keys. And the other downside of virtual nodes is that replication gets more complicated because you want to make sure you don't want to replicate two virtual nodes that are actually the same physical machine, or rather, you want to make sure not to replicate to two different virtual nodes if those virtual nodes are actually the same physical machine, because then you're replicating, but you're not actually getting the fault tolerance that comes from having them stored on independent machines, because that wouldn't provide fault tolerance. So you have to be more careful. in how you do replication. But virtual nodes, like despite these downsides, which are primarily engineering issues, virtual nodes, this way of this technique of hashing a particular physical nodes to many points in the ring, this is how it tends to be done in practice. We're way over time already. Sorry about the late start and the technical difficulties today. So I'm going to wrap up. Um, but let me know if you have questions. On Friday, we're going to have an exciting uh, class because we're going to have some recent grads who are going to come in and do a Q&A session and talk to you about their experience working with distributed systems since graduation. And hopefully they'll also talk about job searching in the age of COVID-19 and other tough topics like that. So I will see you on Friday. Take care.